Today we are going to solve some Leetcode problems. I have 3 windows open here, 3 tabs. Let's see how much we can solve today. Let's start with Tum Sum. Okay, let me read the description. Given an array of integers, nums, and an integer target, return indexes of the two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. Excuse me. Okay, so I'm thinking if we are going to go with a native approach using 2 nested loops to check every pair of numbers, it's gonna result in the time complexity of O of n square. And so in native approach we can just use 2 nested loops to check every pair of numbers, and for each nums of I we iterate through nums of j and check if nums of I is, of course, where I is greater than j. That means we need to start nums of I. We need to start I at iterator I at 0 and j at 1, and check if I is nums of I plus nums of j is equal to the target, and if true we return I and j. So the time complexity would be O of n square here, and the space complexity would be O of 1 because we don't need any extra space. But as you can see in the follow-up question, it's asking, can you come up with an algorithm that is less than O of n square time complexity? So we can go with an optimized approach here. To achieve O of n time complexity, we can use hash map, and we can trade the space for time. We can trade space for time by using hash map to store the numbers and their indices. So here the idea is that, like, for each number nums of I, we need to find if there exists another number target minus nums of I in the array, in the other array. And instead of searching the array which takes O of n, we use a hash map to check this in O of 1. So this is how it's gonna work. First I'm gonna create a hash map to store each number as a key and its index as the value. Then I'm going to iterate through the array once, and for each number nums of I, I'm gonna compute the complement, that is target minus nums of I, and if the complement exists in the hash map, we found the two numbers that sum to the target, and we return their indexes. If not, we add nums of I and its index to the hash map. And the key is, since we are guaranteed exactly one solution and cannot use the same element twice, we only add a number to the hash map after checking for its complement. And the time complexity here would be O of n, because we traverse the array only once, and the hash map operations are O of 1 on the average. Sorry, excuse me. And the space complexity here is of n to store up to n elements in the hash map. And why you can wonder why this hash map works, because hash map allows constant time lookups for the complement, and by storing the indices we can directly return the record output. We avoid using the same element twice because we check the complement before adding the current number to the hash map. Okay, let's start coding now. First, I'm going to initialize the hash map. Sorry, this is I. Okay, let me run this. Okay, this. Okay, let me connect to the internet. Line 14, yeah, we missed a semicolon there. Okay, this sounds good. So, as I said previously, let me walk through the code. Here we are having an hash map to store that maps each number to its index to store the number to index mappings, and then here we are looping through the nums using index I. Just okay. And then we are finding the complement here. So for nums of I, we are computing the complement, which would be target minus nums of I, and then we are checking the hash map. We are using contains key or complement to see if we have seen a number that when added to nums of I equals target, and if we found such a number, we are returning map.get complement comma I. So here, yeah, and here map.get complement, get a map.get complement, it's gonna return the index of the complement, and I is the current index. And then if there's no match, we are gonna add the nums of I to the nums of I and I to the hash map with here the number and this index, and then we are, if the problem, even though the problem guarantees a solution, so we'll never reach this, but it's included for completeness here. So here we are returning an empty array if in case there's no solution found. And okay, let's move on to the next Leetcode problem, which is 3 sum. Here it says, let's read the problem statement. It says, given an integer array nums, return all the triplets nums I, nums of j, nums of k, such that I is not equal to j and I is not equal to k and j is not equal to k, and nums of I plus nums of j plus nums of k is equal to 0. Notice that the solution set must not contain duplicate triplets. So here let's talk about this problem. Here we could use a native approach, which would be like using 3 nested loops to check all possible triplets I, j and k, where I is less than j and j is less than k. That means we are starting with I is equal to 0, j is equal to 1, and k is equal to 2. And if nums of I plus nums of j plus nums of k is equal to 0, we add the triplet to the result. To avoid duplicates, we can store the triplets in a set, that is sorted triplets as a string or tuple. So, but the drawback here is the time complexity would be O of n square, so which is impractical for n up to 3000, that is like up to 27 billion operations. And so that's why we avoid it, because this is too slow, and we can do better by reducing the problem's complexity. So the optimized approach here would be to reduce the three-sum problem to a two-sum problem for each element, using sorting and two pointers to handle the two-sum efficiently. So the steps would be, first we need to sort the arrays. Sorting allows us to handle duplicates easily, and we can use two pointers effectively. So sorting takes O of n log n, and then we can iterate over the first element. For each index I, we treat nums of I is the first number of the triplet, and then we solve the two sum for the remaining two numbers. We find the numbers in the subarray, and nums of I plus 1 to n minus 1, that sum to nums of I, since nums of I and nums of j and nums of k is equal to 0. That means we have like nums of j plus nums of k is equal to minus nums of I. So we can use two pointers for two sum. We can initialize two pointers. Left is I plus 1 and right is n minus 1. And when left is less than right, we compute the sum nums of left plus nums of right, and if it equals minus nums of I, then we add nums of I, nums of left, and nums of right to the result. If the sum is too small, we increment left to increase the sum, and if the sum is too large, we decrement right to decrease the sum. And we can handle duplicates. We can skip the duplicate nums of I value to avoid duplicate triplets. And after finding a valid triplet, we skip duplicate nums of left and nums of right values to avoid duplicate pairs. So here the optimization is, if nums of I is greater than 0, it breaks early, as all subsequent numbers are non-negative. So, and because the array is sorted and their sum cannot be 0. So here this approach works because sorting ensures we can use two pointers to find pairs O of n in O of n for each I, and the two pointer technique avoids the need for a hash map like Tum Sum, which could complicate duplicate handling. And we can skip duplicates, ensuring the output contains only unique triplets. And so let's start coding. So okay, so first I'm going to initialize the result set. Actually, it's a list. Okay, let's run this code. Okay, and yeah, that's good. So now I'm going to explain how this code works. So here I'm initializing the result list, and then I'm sorting here arrays dot sort sorts the array in o n log n. Let me just write this here. And here we are iterating over each possible first element. So this is going to be the outer loop. I is equal to 0 and I is less than equal to nums dot length minus 2 and I plus plus. So here the outer loop is going to go from I is equal to 0 to n minus 3 because we need space for two more numbers there, the j and k. and then we are skipping for duplicates. And if nums of I is equal to nums of I minus 1 and I is greater than 0, we are skipping to avoid duplicate triplets. And here we have early termination. If nums of I is greater than 0, we are breaking and going out of the loop. And because a sorted array ensures all subsequent sums are positive, and then we have two pointers here. So left is equal, left is going to be I plus 1 and right is going to be nums length minus 1. And so we are going to compute, when left is less than right, we are going to compute sum, which is going to be nums of I plus nums of left plus nums of right. And if sum is equal to 0, we found a triplet and we're adding it to the result results list of list. So here we would have add arrays dot ask list and nums of I, nums of left and nums of right. And we are skipping for duplicates if while left is less than right and nums of left is equal to nums of left plus 1, we are incrementing the left pointer. And we are skipping duplicates for right while left is less than right and nums of left is equal to nums of right is equal to nums of right minus 1. We are decrementing the right pointer. And here we are moving the pointers left and right. And if sum is too small, we are increasing it, and if sum is too large, we decrease it, and then we return the result. So here the time complexities is for sorting, we saw that it's O of n log n, and for outer loop O of n iterations, and for inner two pointer loop we have O of n per iteration, because left and right traverse the array once. And so it's going to be O of n log n plus n square. So it's going to be O of n square. And let's walk through an example here. So first we are going to sort the array. So that's going to be, the sorted array is going to be -4, -1, So for sorting, the time complexity is going to be now let's iterate over I. We are starting from I is equal to 0. So let's say what happens when I is equal to 0. Nums of I is going to be, that is nums of 0 is going to be -4. But what we want is minus nums of 0. So that's going to be just 4. And then what's going to be left and right? So left is going to be 1 and right is going to be 5. As we can see, left is the second element here. Left is I plus 1 and right is the last element. And while left is less than right, sum is going to be nums of 1 plus nums of 5 is equal to nums of 1 is -1 and 2. Is equal to 1, which is obviously less than 4 here. So what happens if it's less than 4 while left is less than right? Yes, that's correct. And nums of left, we still haven't achieved that. Nums of left plus 1. What is nums of left plus 1? That is -1. No, we still haven't achieved these conditions. And No, actually we have here, as we can see, that nums of left is equal to nums of left plus 1. So we are incrementing left, so left is going to be 1 plus 1, that's going to be 2. And now we are continuing, yeah. But this is only if sum is equal to 0. So here we are going with sum is not less than 0 here. It is less than 0. So we are incrementing the left, and then now sum is going to be because left is 2 and which is minus 1 and plus 2 again. So you see it's going to be 4 and it is less than 4. It's going to be 1 and which is less than 4. So we are incrementing left again. So left is going to be 3. Okay, so now again we are incrementing left now. So that is going to be 1, 2. So again we are incrementing left, so left is going to be 5. Now left is equal to right, so we are exiting the loop. And no triplets found. Next we are going with I is equal to 1. And nums of 1 is equal to -1. So now the target sum is going to be minus nums of I, which is 1, and left is going to be here left is going to be 2 again, and right is going to be 5 again. Yes, it equals the target sum. So we are adding the triplet. To the result, and then we are skipping the duplicates. So left is going to be 3. And nums of right is equal to 2. Okay, no duplicate. Which is equal to the target sum. So we are adding the triplet. To the result and skipping the duplicates. Okay, left is greater than right here, so we need to exit the loop. Now I is going to be 2 and nums is going to be nums of 2 is going to be -1. Yeah, that's right. And yeah, so here we need to skip and continue with the loop. So we need to skip to avoid duplicate triplets. Now I is going to be 3 and nums of 3 is going to be 0. So here the target sum is going to be minus nums of 3, which is 0, and left is going to be 4, right is going to be 5. So here we are decrementing right. Now we have I is 4 and I is greater than or equal to n minus 2. So that means we stop the loop. Yeah. So the final result is going to be we have 2 lists and here's one. And here's the other. Okay, see you in the next video.